in front of us right now we have got a stress strain diagram. We can see here in this stress strain diagram what we have got. We have got stress shown over here. This is sigma, and this is what, this is your strain, right? Stress strain diagram is there. Now here there are certain areas, we can see it very clearly. So what are those areas? Let me just mark it out. Which is the plastic zone, which is the elastic zone. This is the elastic zone. This is elastic. Okay. Beyond this one, it is what? It is plastic zone. This is plastic. What do we mean by elastic and plastic? Elastic zone is that zone, if you remove the force, then what will happen? The material will regain its original shape. Okay, that is what is the elastic zone. See, this is elastic zone. Understand? So strain is what? Strain is nothing but delta L over L. Stress is what? Force divided by area. This is what is stress. Correct, Shivam? Okay. Now you can see here, as we start loading the component, what will happen? The material starts from here, from 0. It goes up to this point. I will call this point as A. Okay. This point is called as yield point. What do we call it? Yield point. So that is, at this point the material will start changing from elastic to plastic zone. Okay. A, and this is called as B. I will call it as B. This is the point where I will call it as C. This I will call as D. Okay. I can call like this, or I can even change the shape. Let me just remove this one. I will do it the other way around. So what I will do, I will just go back. I will call this one as A, B, C, D, E. Okay. B is what? B is upper yield point. Okay. B. C is what? C is lower yield point. Okay. Then what I have got? I have got D. So D is ultimate load. Understand? Ultimate stress, or even we call it as strength. Okay. And E is what? E is breaking point. Okay, breaking stress. So see here, if I come from here, if I start marking like this, I will mark it as what? I will mark it as sigma y. If I go here, I will mark it as what? I will mark it as sigma ultimate. Okay. From here, if I go, I will mark it as what? Sigma. I will write it here. There is no space. Sigma B. That is breaking stress. Okay. Now you can see here between A and B, it is a straight line, is it not? So this will be what? This will be, if I draw at any point two lines, the slope is constant, whether it is here or whether it is this point or the whole triangle. What can I say? Slope is equal to dy by dx. What is dy? Dy is nothing but sigma. Dx is what? Strain. Okay. The slope I call it as E, which is Young's modulus. Stress is proportional to strain, or I can say E is equal to sigma by E. It is constant within the elastic limit. This we call as what? This we call as Hooke's law. What does Hooke's law states? Hooke's law states that the stress is proportional to strain. Okay. This is what we say. Now, let me add one more slide here. I will add one more slide, insert a blank slide. Okay, now I will take this slide here. Right, I will take this slide. I will just remove this portion. How do we do it? cut it and remove it. I'll just make it little. Even this also I will cut and remove so that I can write something there. Unable to do something here. I don't know why. Okay, let me just write something here. Okay. So now I will just go here. I will just review. I will just go here. I will start thinking. I will start writing it with a pen. Okay. Now let us see here. What can I do now? See, for some materials, what will happen? For some materials, you have a very clearly defined strain, like what you had just now, like this. Okay, so here there is yield point, you can see very clearly. But there are certain times we have got a graph. In that graph, what happens? You do not see any strain. Very clearly, you don't see it. It will be just like this. So in such situation, how do we find the yield point stress? That is by offset method. Offset method. In this method, what actually we do? We do 0.2% offset. Let us say, if I am having 0.1 here, 0.2, 0.3 like this. This is what? This is your strain, is it not? This is your stress. So 0.2% offset means what? This is 0.2 divided by 100, is it not? 0.2 divided by 100 will give you how much? 0.002, isn't it? So now what I will do is, so I will just say this is 0.1. This will be how much? 0.05, correct? So now again, if I divide this one, somewhere I will have 0.002. Again, I will divide 10 times, somewhere I will have 0.002. From here, I will draw a line which is parallel to this line. Understand? I will just draw a line like this, which is parallel to this line. So it is going and cutting at this point. So from here, I will come. This is my sigma y. This is what is percentage offset method. Understand? When you cannot see the yield point clearly. For ductile materials, mild steel, you see something like this. It's very clearly it is there. So you can easily find out sigma y. Okay. So this is about the nomenclature for ductile materials. Still, see, you will be given a graph like this. Then you need to mark A, B, C, D, E, and just write what is stress, what is strain, which is elastic limit, which is plastic limit. See here, after your oh sorry, it just moved out. Sorry, extremely sorry, it just moved out. I don't know how do I get it back. Okay, I think it was somewhere here. Fine. Okay, so now actually what happens now, if you see here, after the I think I have to move it a little bit like this. Yes, I believe it might be here. Yeah, it is here somewhere. Okay, so now see here, from D to E, the curve is sloping like this, is it not? The curve is sloping. Okay, so this portion we call as what? This portion we call as necking. Necking will be very clear in mild steel specimens. In other specimens, necking will not be there, as we saw in other graphs. Okay, this is regarding stress strain curve, and in your quiz we will definitely ask you this.